Greetings to all, welcome to the channel Simtech05. In today's video also we'll discuss about the implicit and explicit analysis. The twisted plate problem is solved by the explicit step as you can see here in the left hand side, and same problem solved by the abacus standard, or we can say with the implicit solver. Of course the implicit solver comes under abacus standard, so here it is visible as a abacus standard. So the final results, as we can see, the difference is very less. In explicit, the maximum result, or we can say the maximum stresses are around 516.89 GPA, and here 524 GPA. And if you want to compare results increment to increment, you can see here. So this is the first increment. Let me modify the result visibility, the limit, and not the first and last limit. Recompute the limits. Click on OK. Now you can see. Okay. So this is the zeroth increment, and in the zeroth increment, of course, the results or stresses are 0. The first increment 143 by explicit and 145 by implicit. So we are quite closer. Okay. Of course, those are the two different techniques. We will never get the same results for moderate and complex type of problem. Yes, if problem is quite simple, then we may get same result. But if your problem is moderate or complex, you will get a little difference. Here you can see for the third frame, maximum stress is here for the explicit 147 and here also 147. But still we have difference in the points, and so on. So let me play the simulation and you can see how beautifully both implicit and explicit solver are able to complete the simulation. Okay, not only the visibility or not only the animation point of view, but results are accurate in terms of reaction forces and energy balances also. So this is the third video of the sequence. In first video, I talk about the implicit explicit analysis, differences, algorithm they use, and a comparative study basically. In second video, I completely digged into explicit analysis algorithm, how mathematically this algorithm works, how it begin the solution, and how solution populated. And these two analysis, of course, the quasi-static analysis, the kinetic energy is very less as compared to the internal energy. So if you want to learn more about the quasi-static analysis, for that also I already uploaded two videos. Quasi-static analysis in Abacus FEA part 1 and part 2. One more important point I want to show you here. In the explicit step, total number of increment around 94,000. And here only 1500, around 1500 or 1400 increments. So difference in increment is huge, and on the basis of increment one can easily predict or judge that explicit analysis take time to solve the problem as compared to the implicit solver, but that is not true. We will see why and how. So before that, let me compare the energies, energy balances. So go with the create XY data options, ODB history output, continue, and say artificial energy, kinetic energy, and internal energy. And let's click on the plot. So for the both implicit and explicit, those energies are plotted, and here we can see, let me change the visibility of the plots. Say internal energy and internal energy, those thickness of the lines I want to change. So you can easily predict this is internal energy for the explicit step and this is for the implicit step, and we can see the only internal energy is dominant in the system. So we can say those are the quasi-static, or the simulation is quasi-static simulation. It's mean the problem can be solved by the quasi-static as energy, kinetic energy is very less. So we are solving our problem, same problem with implicit scheme as well as with explicit scheme, and we got the similar kind of result. And at the same time, we verified that problem can be solved by the quasi-static technique because the kinetic energy is negligible as compared to the internal energy. And let me plot for reaction force also. So this is my stationary tool and this is my rotating tool. So on the stationary tool, I have reaction force on the reference point actually. So let me go with the feature edges, click on apply, OK. Still the reference point is not visible clearly. So yeah, let me rotate little bit. Now we can see this point. Go to again XY plot options, ODB field history, because I did not gone for any request, reaction force request on the reference point. So ODB field, continue, make sure you click here on this window and say unique nodal if you are having some other options, and say reaction force and only magnitude I want to plot. Go with the edit options, add, and select this node precisely. Okay, you may need to go with the zoom in. Yeah, select and click on plot. So this is the reaction force for the explicit model. Here you can see this is the ED, explicit dynamic model, and now click on the implicit dynamic model. Again, variable are the same, reaction force, make sure magnitude only, and add to selection. Yeah, edit selection and precisely select this reference point. Then click on done and plot. So let's dismiss, and this is my animation pointer actually. When you click on play it will change. Okay, so no need to worry about that. Go to the fit in all, and here also you can see the maximum reaction force shown by explicit is also around 5.5 e raised to the power 3, and for the implicit also approximate same. Okay, so what it's mean, we can solve the one problem with implicit technique, with explicit technique. Even the problem that I shown to you can be solved by the general static step also, but convergence is the important parameter there, and one more important parameter, that is the simulation time. So we will see the simulation time, we will discuss on the simulation time. Go to the standard view and let's try to model this in the abacus. Okay, now we are in the abacus assembly, and you can see here ED is nothing but explicit dynamic. Here we have two part, one is the plate part and tool part. Let me show you here. This is the plate one and this is the tool one. Okay, I'm going to use this tool twice, so no need to create one more part. And this part I selected as, here you can see, discrete rigid part. Okay, so make sure this is the surface component, otherwise in the assembly it will be showing the error message. And one reference point also I created for the same. Click on cancel, then click on property. So of course for the rigid part there we not need any property, but for the plate part we need a material. So general elastic plastic material with density I defined, not exactly aluminum but some type of aluminum material property I considered. 3800 e raised to the power minus 12, that is the density. Then elasticity, or we can say Young's modulus, 70 GPa and Poisson's ratio, and then plastic material data. At 140 gigapascal, strain is 0. At 600, it will be 0.5. So this material data I considered and property assigned. Okay, assembly also is easy. I'm not going to waste the time in the assembly. So you can easily use these options, translate and rotate, and can assemble the these two tools, or we can say these two cylinders with respect to the plate. So go to the step. So first we want to solve the problem with explicit dynamics. So create a step. Sorry, that's not a step. This is our step manager. Click on create and say ed, let's say explicit dynamic and time period. As this is quasi-static problem and I'm considering increased load rate technique here, so my problem will still remain in the quasi-static mode and the kinetic energy will not significantly change. If you're not aware about the increased load rate technique, please go with the quasi-static analysis video part 1 and part 2. So I'm taking here 0.01. This is my time. Nonlinear geometry checked on, automatic increment, no mass scaling I'm going to use. Click on OK. And then the most important part, that is the output request. Why it is important? Because I want the output request exactly after the particular time, or we can say we want output request in evenly spaced time interval, not the approximate. We want at exact time. So click on the exact options and define here, 40. These are number of frame, nothing but number of frame. These 40 frame I want in the output request, and default output parameters, and click on OK, click on dismiss. And if you want to modify, here also you can modify. For the history output, by default it is 200. It's sufficient large. So step is completed. Now interaction. Okay, I already created surfaces, and you can see here I also create a split. Let me go with the part and see. Because my rollers will be in the contact with this region of the plate, so I split it from here, that easily I can define the contact surfaces. And in the assembly you can see I have here surfaces. So this plate 1 surface, and with respect to that I have plate 1 and tool 1. Okay, this one is tool 1, plate 1, tool 1. These are the connecting surfaces. Plate 0, tool 0, these are the another connecting surfaces. So these are rigidly connected to each other. So I can say here in the interaction I have to define the tie connection. So I can say tie 0, and let's say surface region from the surfaces, existing surfaces. So your tool is rigid one, so you have to select tool surfaces as, or we can say cylinder surfaces as a master surface. Tool 0, I think this is tool 1, tool 1, continue, again surface region, and plate 1, click on continue. And I don't want to adjust the slave surfaces. Here these plate surfaces, plate nodes are the slave nodes, so I don't want to adjust those slave nodes. So I uncheck, click on OK, create one more tie connection, tie 1. Simulation is quite easy, but with respect to this simulation we will get a beautiful comparison between implicit and explicit. Of course, the selection of implicit and explicit step depend on number of parameters. Those I explained in my first video. Please go through that. So here tool 0, surface, and plate 0. So why we are trying to perform the same simulation with two steps? Because I found many people having misconception about that. Even the industrial people think like that. Few days back just I attended one seminar and someone says like explicit is for dynamic simulation and implicit is for non-dynamic type of problem and creep and swelling type of problem. Is partially true. In implicit we can solve the creep and swelling very easily, but in general static step we cannot. But it's not mean we cannot solve the dynamic analysis in implicit step. One more wrong statement I found, that quasi-static technique can be used only with the explicit step. No, quasi-static technique also available with implicit scheme. Even we can say quasi-static not available with the explicit, but we are utilizing the quasi-static technique for the explicit step. But for the implicit step, the quasi-static is separately available. So these ties are created, and then go with the load, create load. Okay, first I'm going to make a fixed boundary condition, symmetry and initial, and let's say fix this with respect to reference point, select from the viewport, encaster, and create displacement, and say the displacement is exactly rotation. So displacement at this reference point, and say initially these displacements are 0 0, and now I can modify from the second step. Okay, so rotation about this z axis here, and this rotation, say I want to rotate this tool or cylinder 3 times. So here the values are in the radian. Okay, so what you have to do, one rotation is complete in 2 pi, so we can say 6 pi. So simply 6 into pi, or you can feed the value of pi, or you can write down the pi. So amplitude you need to create, go with the amplitude. Yeah, already I have one amplitude here, that's why it is showing amplitude 2. So either you can go with the smooth step, or you can go with the tabular formation also. At the time of 0, my amplitude is 0. At time of 0.01, my amplitude is 1. This is my total time period. And amplitude 2 that we just created, click on OK. So if you double click on that, again this value will be automatically considered. That's all. Then you have to go with the mass, say mass for this part. Okay, as this component going to be twist, or we can say it's subject to the bending load along its thickness. So minimum 3 element we need along the thickness. If you want to define the more number of element along thickness, you can define, but as we will increase the number of element along thickness direction, the size of the element will reduce, and we can say the stable time increment will be reduced, and our total simulation time will be increased. So yeah, 1 is sufficient global element size, and here I defined 3. I already defined in previous run, so I'm not going to define it again. Let's say mass and click on yes. So very beautifully you will get this element. Same for tool, make sure the element size is 1. Okay, and go with the mass. No need to worry about the mass of the tool component or the cylinder component. Go to the assembly. Now you can see very beautifully software having mass for the plate component and tool component. So after massing, just go with the job. These jobs are already created, so I'm going to delete these jobs, and let's save the file in different folder. So this is twisting problem and twisting 2. So this twisting model is already done. So plate twisting, and say job with explicit dynamic, continue, parallelization, number of cores 16, and click on OK. And now click on submit. And now go with the step. Yeah, I'm going to copy this model. I'm not going to replace this step. Let's say copy this, copy model, and this is the ID, implicit dynamic, and whatever modification I will do in implicit, that will a different model actually. It will not make changes in the first model. So click on replace dynamic implicit, continue, and say time of 0.01, nonlinear geometry on, and initial size and minimum 1, and say for safe side it's took around 1500 increment. So for safe side I'm taking here 10,000 maximum increment and click on OK. Make sure you have the same frequency output. Okay, otherwise you are unable to compare the result at the same frequency at the same frame. Okay, so here also please make sure evenly spaced time interval. Make sure exact time interval, okay, not the approximate time interval, and number of interval, same number of interval, those are defined in the explicit step. Okay, and that's all. Save the file. Everything is already created, so interaction already done, load, force, massing, everything is already done, and here you can monitor the explicit step and this going on, and you can see how fast this solving your increments. You can see around 2000 increment software going to solve in few seconds, in 2 or 3 or 5 seconds. So in this way we can see the explicit step taking small increments, huge number of increments, but the speed of the solution are also very fast. Why? Because it's a direct solver, it's not a iterative solver, it's not going to iterate the solution and come to the exact solution and then proceed for the next increment. It's a direct solver. And how it do? It do by making inversion of the mass matrix and the damping matrix. If you want to know more about, please go with the implicit and explicit video. So let it complete. Okay, this explicit step is completed, and in status we can see here the wall clock time. Okay, this is around 307, so the exact time to solve the problem. And sometimes we also consider the system time, so it's around 310 or 310 seconds. Let's minimize and go to create one more job as implicit dynamic with the implicit dynamic model. Continue, parallelization, number of cores, same number of cores I'm assigning 16. Click on OK and click on submit, and now again click on the monitor, and you will see how slow this solver is to solve an problem. Okay, so it's another time for the first increment of 1 into e raised to the power minus 4, then it try to attempt for 2.5 e raised to the power minus 5, and then even it is unable to attempt for 6.25 e raised to the power minus 6. So it's taking or it's converging the solution for very less increment value, very less time increment. So in this way you can see it's start solving for the increment size of e raised to the power minus 7, and it will take huge amount of time. Why? Because at a time it's solving only one increment and the increment size is very small. It's the same as explicit increment size, but explicit step or explicit solver solving number of increments at a time, and here it's solving only one increment at a time. Increment values approximate remain same for the both cases. Let's see here. So this is explicit one, and okay, let me open. So you can see, say step time is around e raised to the power minus 7, and initially for that also stable time increment or step time is e raised to the power minus 7. But you can see in the first attempt itself, software able to solve these much number of increment, and this solver, implicit solver, solving only one increment, so it will take huge amount of time. So I'm not going to solve it completely because I already solved the problem and I have the results. Let's kill it and let's save this model. So here in the implicit dynamic you have to open the STA file, I think, and go with the not STA. It shows the total number of increments successfully completed but not shows the wall clock time or time taken by processor to solve. So go with the message file, and in the message file, yeah, here you have wall clock time. These are like 5600 second, and if you go with the explicit step, this is the ID3R means implicit dynamic 3 rotation and time is 0.01, and same for explicit dynamic 3 rotation, time is 0.01. So again STA file I have to find here, and you can see the wall clock time is only 219 seconds. So in this way we can see so on the basis of these results, as we can see here, implicit and explicit both are giving you quite accurate result. Kinetic energy is approximate zero in the both cases, or we can say those are the both quasi-static near to the experimental one. So we can say both are able to solve such this type of problem. Not only this type of problem, they are capable to solve many of the problem with higher accuracy, with similar kind of accuracy, but they have their own constraints, own restrictions. Like implicit cannot deal with complex contact condition and huge amount of deformation, and as we can see here, implicit able to solve the large deformation in this case, but it took lot of time. And on other hand, the explicit step may not able to solve large event problem. If we talk about the creep and swelling, those are the, say, large event problem. Okay, the problem itself take around hours and days to complete it. The event not completed in seconds, it's completed in hours or sometime in days. So it is impossible to solve with explicit step that time. Okay, so hope you got a clear idea about implicit and explicit. So few more analysis I will run through both step implicit and explicit, and I will update in the another video. So thank you for listening. If you have any query or question, you can ask me in the comment section, or you can join us on Facebook, on Telegram, and you can ask the questions there also. So thank you all.